1.6, calculating limits using the limit laws. So that's a problem that we have. A lot of times the problem is find the limit, and they give you this crazy function. Well, limit laws are what we need to use oftentimes to do that. In this section, we use the following properties of limits called the limit laws to calculate limits. Now, we're going to suppose that c is a constant and that these limits exist. Limit as x goes to a of f of x and the limit as x goes to a of g of x. Then we have these 5 limit laws. They have to do with finding the limit of some combination of functions arranged in a certain way in terms of simpler limits. These 5 laws can be stated verbally, which is oftentimes, for a lot of people, very useful, extremely useful. The sum law. The limit of a sum is the sum of the limits. So, as an example here, limit as x goes to a of a sum f of x plus g of x is the sum of the limits. The sum of the limit of f of x as x approaches a plus the other simple limit. Limit as x approaches a g of x. And in a way that you would expect, the limit of the difference is the difference of the limits. So we could replace the plus signs with minus signs and we would have another law. The limit of a constant times a function is the constant times the limit of a function. In other words, you can move a constant c into or out of the limit. Right? If you have limit and there's like a number like 5, c times f of x, you can take that c right out of there and multiply that by the limit. Or you could go the other direction. You could take the constant on the outside and put it on the inside. Limit of the product is the product of the limits, not surprisingly. In quotient law, not surprisingly, the limit of a quotient is the quotient of the limits, but of course you can't have the limit in the denominator equal to 0 because you can't divide by 0. For instance, if f of x is close to L and g of x is close to m, it is reasonable to conclude that f of x plus g of x is close to L plus m. That, of course, would be the sum law. Use the limit laws and the graphs of f and g in Figure 1 to evaluate the following limits if they exist. So we want to know what is the limit as x goes to negative 2 of the sum of f of x and 5 times g of x. Okay. Well, we also want to do part B, get the limit as x approaches 1 of the product of the two functions, and in part C we want to get the limit as x approaches 2 of the quotient of the two functions. And so this is just going to become a problem of finding the simple limits, using the limit laws, rewriting the expression, getting the simple limits, and doing the arithmetic. Okay, so from the graphs we will calculate these limits. Okay, we will need the limit as x goes to -2 of f of x. Okay, well, as x approaches -2, either from the right or to the left, not at -2, but again that doesn't matter, f of x is 1. And g of x has a value of -1 at x equals -2. Therefore, we can take these numbers, 1 and -1, and after using the limit laws, do some arithmetic and get an answer for this problem, limit as x goes to -2 of the sum of f of x and 5 times g of x. Using the limit laws, limit of a sum is the sum of the limits, so we break up the limit that way. Now we have two limits. They're simpler, and of course this constant 5 is going to come right out of the limit, and then we'll replace all of this with 1 and the other thing with -1. Okay, so the 5 comes out. The first limit is 1, the second limit is -1. We do the arithmetic and we get an answer of -4. Because we see that the limit as x goes to 1 of f of x is equal to 2, okay, we can see that. But limit as x goes to 1 g of x does not exist because the left hand and right hand limits are different. Okay, the limit as x goes to 1 of g of x is -2, but the limit as x goes to 1, the right hand limit is 1. The left hand limit was -2. The right hand limit is -1 because this endpoint here is the point 1, -1. So that's how we get this -1 right here. So we depending on which limit laws we use, we could have a problem. We can't use law 4 for the desired limit because, you know, we can't talk about the limit as x approaches 1 of g of x in any limit law because that limit does not exist. This limit here does not exist. We can use law 4 for one-sided limits. You know, if we wanted to do that, we could do that. Again, the right-hand limit is for g of x is -1, the left-hand limit is -2, so we could use those numbers in limit laws. So if we wanted to ask, okay, what is the limit as x goes to 1 from the left of the product, then we could say, okay, well, we've got the 2, and we've got the -2, so that would be -4 for the limit as x goes to 1 from the left of the product. And from the right, then we would use this -1 instead, along with the 2, to get -2. The left and right limits aren't equal, so the limit as x goes to 1 of f of x g of x, without anything, you know, up here, no left hand limit, no right hand limit, it's just going to 1, simpliciter, does not exist. The graphs show that the limit as x goes to 2 of f of x is approximately equal to 1.4. As x goes to 2, f of x goes to a number that's approximately 1.4, g of x 0. And so the limit laws will be used and those numbers will be substituted. Now, of course, not all the limit laws could be used when you've got one of the limits as being 0. We cannot use law 5. The given limit does not exist because the denominator approaches 0 while the numerator approaches a non-zero number. So if we were asked to find the limit as x approaches 2 of the quotient function f of x over g of x, well, we would just have to say that that does not exist. If we use the product law repeatedly with g of x equals f of x, we obtain a new law. Okay, so product law, limit of a product is the product of the limits. The limit as x goes to a of the product f of x times g of x. Well, the product law says that that is the product of the limits. Limit x goes to a f of x times the limit as x goes to a g of x. Now, if we use it repeatedly with the two things equal to each other, then what do we have? We've got limit as x goes to a f of x times f of x, because the two are equal. And by the law, by the product law, that's limit as x goes to a f of x times itself. In other words, the square of the limit as x goes to a of f of x. Well, we totally could do that any number of times, right? I mean, we didn't have to limit it to just 2 factors of f of x. We could have had n factors of f of x. Then we would have n factors of the limit, and therefore the nth power of the limit. Okay, so limit of a product, limit of a power is the power of the limits. In applying these 6 limit laws, we need to use 2 special limits. The limit as x goes to a of a constant just is that constant. Okay, I mean, it's not a big mystery. You know, if your function of which you're taking the limit is a constant function, you know, it's got a graph, which is a horizontal line, you know, well, as x approaches some number a, you know, f of x is going to approach that number c, whatever it is, so it couldn't be anything else. The limit as x goes to a of the function just x equals the number a. Okay, so if the function is just x, in other words, you have the identity function, we end up with just a, so it's kind of like a is substituted for x. These limits are obvious from an intuitive point of view by looking at these graphs or stating them in words. If we now put f of x equals x in law 6 and use law 8, we get another useful special limit. So this f of x right in here, that's going to be the function, the identity function again, just x. Okay, so limit as x goes to a of x to the n is a to the n. And similar thing holds for roots, because a root is a power after all. So limit as x goes to a of the nth root of x equals the nth root of a, where n is a positive integer. For n even, in order for this to be true, we will have to assume that a is positive, because for n even and a not positive, or for n even and a negative, the root doesn't even exist, because we are dealing with reals here. More generally, we have the following law, a root law. Limit as x goes to a of the nth root of f of x is the nth root of the limit. The nth root of the limit as x goes to a of f of x. The limit of a root is the root of the limit. Now, here's where it's getting really important. Direct substitution property. If f is a polynomial or a rational function, okay, so that's a very important qualifier there. If f is a polynomial or rational function, so polynomial function, it's a sum of ax to the n's, ax to the n's. Let me rewrite that. A sum of ax to the n's, okay, so like 5x squared minus 2x plus 11, or a rational function, that is a fraction of those kinds of things. A rational function is a function that can be written as polynomial 1 over polynomial 2. So that's the kind of function we have here for f of x. A is in the domain of f, then f of x, the limit as x goes to a of f of x equals f of a. Okay, now you're like, okay, well, what's the big deal about that? Well, that's going to introduce us to a whole new category, a whole new matter that is hugely important and essential in calculus. Okay, functions with this direct substitution property are called continuous functions at a. They're called continuous at a. Okay, and so the issue will be what can we say about such continuity with respect to certain kinds of functions? When is a certain kind of function continuous at a number? When is it not? What if it's continuous at a lot of different values of a? In fact, a connected set of values of a whole interval of values of a. In general, we have the following useful fact. If f of x equals g of x, when x is not equal to a, then the limit as x approaches a of f of x equals the limit of x as x goes to a of g of x, provided the limits exist. And we'll continue talking about continuity